All right, so we're in section 4.6, part 2. So someone asked me in the last class, they said, why is cosecant the reciprocal of sine rather than cosine? Wouldn't it make more sense the other way? And I said I would try to figure that out, try to find that out. I'm guessing it has something to do with the Greek names that they were given, some kind of language thing that why those names were that way. So it sure would be easier to keep straight in your head if cosecant went with cosine, but it doesn't. All right, so let's look at our reciprocal identities for secant and cosecant. We know that secant theta is 1 over cosine theta, and cosecant theta is 1 over sine theta. So we're going to graph these functions. So we're graphing these fractions. So following from what we talked about on Friday, what is going to happen with these graphs? What do we have to be aware of?
Where sine theta equals 0.
Sine theta equals 0 for cosecant, and where cosine theta equals 0 for secant. So that's going to make our function undefined and give us what on our graph? A vertical asymptote. So each of these is going to have vertical asymptotes. So we're going to get vertical asymptote. When cosine theta equals 0, and this one's going to give us vertical asymptote when sine theta equals 0. So from our graphs, we can graph sine theta and cosine theta, and where they're equal 0 is where they're crossing the x-axis. So that's going to make sketching our graphs really easy. And the fact that we're taking a reciprocal, secant is going to have a maximum where cosine is a minimum. And it's going to have a minimum where the cosine is maximum, because we're taking the reciprocal. So we're going to have minimums and maximums at the maximums and minimums of our, what we're going to call our parent functions. So that makes sketching the graphs of these very easy. Because we have asymptotes, and because we know that the maximums and minimums are at the maximums and minimums of our parent function, at the tops of the peaks and the bottoms of the valleys, then basically we're set. So to sketch these graphs, to graph these, our first step is going to be graph the parent function. And by parent function, I mean for secant, we're going to graph the cosine, and for the cosecant, we're going to graph the sine. So we're going to start by graphing a sine or a cosine function, which we already know how to do. We're going to sketch asymptotes where the parent function equals 0. And that's easy from our graph. It's just where the parent function crosses the x-axis. So we will be able to see right away where our asymptotes go. We're going to put a maximum or a minimum. So we're going to get a point. On top of each peak and at the bottom of each valley. And I'll call it each peak and trough. I guess, and it would be the top of each peak and bottom of the trough. And then all we have to do to complete our graph is then connect that, sketch the graph between the asymptote. So I'm going to sketch a quick graph of a secant function and a cosecant function. So y equals secant theta. I'm going to sketch a graph of cosine theta first. So I'm not going to mark up all my axes. Hopefully by now we're pretty good at this. We're pretty familiar. So I'm just going by pi over 2 units, just like we normally do. So here's going to be my cosine function. There's one period. I'll go back this way a little bit. Like so. Now we'll sketch our asymptotes. Everywhere this equals 0. So everywhere that it crosses the x-axis, I'm going to sketch an asymptote. I have a point on the top of each peak and the bottom of each trough. And then I'm just going to sketch my function between the asymptotes. And there would be, in blue, the sketch of y equals secant theta. So as long as we know what the graph of the cosine function looks like, we're set. And then we can sketch a quick graph of y equals cosecant theta by first sketching sine theta, y equals sine theta. So I'll go through the same process. And sine theta starts at 0 and goes up to a maximum. Sketch in my asymptotes where it crosses the x-axis. Put a point at the top of each peak and the bottom of each trough, and sketch my graph between the asymptotes. And we know, like we talked about on Friday, this is the same. These two are the same, except we're shifted by pi over 2 units. So this starts here at the y-axis. This starts shifted over by pi over 2 units. So we start by graphing our parent function, which we know how to do already. Hopefully we're pretty good at graphing sines and cosines. And then we sketch in our asymptotes, and we're pretty much done. Put a maximum, minimum at the top of each peak and trough, and sketch little parabola shapes between our asymptotes. So questions on the process? Yes?
What was the test that you were basing the parent function?
You don't have to. You don't have to. I usually sketch the whole thing in. So, but some people like to do it just because it makes it look neater. But I wouldn't actually do that. All right. So all I want to do is a couple of examples of sketching a secant and a cosecant function that have some other things going on with it. So nothing that we haven't seen before. So let's look at y equals 2 cosecant x over 2. So we're going to start by graphing y equals 2 sine x over 2. That's going to be our parent function. So what's happening to this graph? You know a equals 2, that does what to it? What is it? Yeah, stretch, a vertical stretch. We know that b equals 1/2. So what does that do to our function? Stretches it horizontally. So we know our period is 2 pi over 1/2 or 4 pi. And I'm going to sketch out my key points every quarter period or every pi units. So here's we can start our sketch. Going by pi units makes it nice and easy. Don't have to deal with fractions. We're going up by 2 units. Now I can sketch this in. We have our parent function is a sine function. So, and I know my graph, my units. Let me move this 4 pi over a little bit so my graph looks a little better. And we'll go back here a little ways to the negative side. So there's my parent function, the sine function. Graph in my asymptotes, sketch in my asymptotes. Get a maximum here, minimum there, maximum here. Sketch those in, and then there goes my graph in between the asymptotes. And there would be my y equals 2 cosecant x over 2. Questions on that one? So if we know how to graph our parent function, we're set. Graphing our parent function is the key. Once we can graph our parent function correctly, then everything else follows. All right, let's look at a secant function. So y equals secant x plus pi. So not a lot going on with this one. So what is this? What's happening with this function compared to our original? Shift by pi units. Which direction? Left. Period is still 2 pi. Our key points are still every pi over 2 units. So we can start sketching this. So we're going to sketch y equals cosine x plus pi as our parent function. So mark my axes with every pi over 2 units, quarter of a period. No stretch, so we're just going up and down, positive and negative 1. And then I'm ready to start sketching my cosine function. Oh, and I need to start shift left pi. And this shouldn't be 3 pi over 2. This should be negative pi. So I need to start shifted left pi. I'm going to start here. And there would be my cosine function. Sketch in an asymptote where it crosses the x-axis. Maximums and minimums. And then I can sketch in my function. And there we go. There would be y equals secant of x plus pi. Questions on that one? So again, grabbing the parent function is the key. Asymptotes everywhere the parent function crosses the x-axis. And then we just put a maximum, minimum on the peaks and the troughs and sketch our function in between the asymptotes. All right, let's see, very briefly, I wanted to mention another kind of trigonometric function. Just, we're not going to go into a lot of detail with these, I just wanted to mention them so you have seen them. We can have a function like y equals x sine x. So instead of a number out front here, I have a function. Well, we can still think of this function as the amplitude. So we call this a damped sine function. So what is the graph of y equals x, this function that's in the front? Stephanie's doing this. It's just a line, right? A line with slope 1 that goes through the origin. So to sketch a graph of this damped sine function, what happens is I have this line y equals x that goes like so. And because sine goes from positive 1 to negative 1, I'm going to graph y equals negative sine x, because sine goes up and down. So this is y equals x, and this is y equals negative x. And then what happens with my sine function, I'm not going to be extremely accurate with the graph, but the sine function is going to go up and down to these lines. So it's going to start here at 0, and it would go up to this line here, and then down, and then here it would go all the way down here because it's getting multiplied by that x value. And then go here. If I go out a little further, it would go all the way up to here. So my sine function ends up looking like this. And it just keeps getting bigger and bigger and bigger. And it would do the same thing going this way. And if I went down further, it would go even further down. And it would just keep getting bigger and bigger and bigger. So this is kind of, we call it a damped trig function, but this one gets bigger and bigger and bigger. And we call, yes? The red line is, it's called the damping function. A dotted, yeah, you could draw it either way. It doesn't really matter. You could draw it either way. So the line y equals plus or minus x is a damping function. And sometimes you'll hear it called the envelope for the function. And it could be any kind of function. We could have all kinds of different functions be our damping functions. One that shows up a lot is an exponential function. So just very quickly, we could have y equals e to the minus x sine x. And what happens with something like this is this exponential function looks like this. So my damping function is this exponential function, and then the sine function would go in between here. And it would end up getting smaller and smaller and smaller and smaller. So our trig function could go in between these damping functions. An example of this that shows up is if you think of a spring, a mass on a spring, and you pull it down and it bounces, and eventually it slows down and slows down and slows down. Eventually it stops. So that would be something like this, where it just gets smaller and smaller and smaller and smaller. If you go on in math and study differential equations, often you get solutions that have these damping factors in the solution, because as time goes on, the things get smaller and smaller and smaller. So there are a couple of problems in your homework where you're matching graphs of trig functions to a damping function. And the idea is that your function gets graphed in between the positive and negative values of your damping function. You can't get bigger or smaller than that damping function. So I just wanted to mention it, wanted you to have seen it a little bit. All right, questions? All right. Homework? There you go. And number 4 and number 51, 53, and 54 have to do with damped trig functions. So just a couple of easy practice problems.